Hello, my name is Gianluca Baldassarre, and I'm giving this presentation together with Emilio Cartoni. We are from the Institute of Cognitive Sciences and Technologies of the National Research Council of Italy. The title of the presentation is Real Competition, Robot Open-Ended Autonomous Learning. This is the first time that the competition is organized together with ICDL in an official way. And it's actually the third time that we hold this competition. So we have acquired quite a notable experience to run it smoothly and to allow everybody to have fun. The competition has a biological inspiration that is much in line with the objectives and targets of the scientific community and the ICDL community. In particular, the competition is inspired by how children learn when they are very young. And the idea is that initially they explore objects and they develop motor skills and knowledge about how objects behave when they act on them. And so they can learn a lot of knowledge and skill on the basis of intrinsic motivations, curiosity, and autonomous learning and exploration. This allows them to accumulate their skills and knowledge until they can manage more complex situations like this one, involving several different objects. The idea is that these capabilities and knowledge that they acquire are very useful because when they become adult, they can use them in order to accomplish activities that are useful for them. For example, they can work and get a wage and so on. So the grand view behind the competition is that we can do the same thing for robots. So the idea is to take a robot, throw it in an environment like this one for a long time and leave it alone to acquire as many skills and knowledge as possible. Then to come back and exploit the knowledge that the robot acquired to ask it to accomplish our goals. For example, here we can put the robot in front of this situation and ask the robot to change the environment to bring it in this other situation that we initially show to the robot through a picture. So this is called an extrinsic phase. And the idea is that the robot should solve this problem on the basis of the knowledge acquired in the first phase, intrinsic phase. This technology that would be developed through solving this benchmark and similar situations that are more complex than the benchmark, so in general, open-ended learning, is very important for applications. For example, it could allow us to have robots that are able to face this kind of environments. These kind of environments are highly unstructured and they're interesting because they pose challenges that are unpredictable at the same time, because it's impossible to envisage all situations that the robot might have to face in these particular conditions. So the key idea is that we will develop an algorithm. We will develop algorithms through this competition that are able to deal with any one of these environments, because the robot will gather knowledge and skills that are suited to the particular environment where the algorithm is run. Getting more into the competition details. So this is based on a pi-bullet simulation of a KUKA arm robot that also has a gripper. And the simulation simulates the gripper touch sensor and also a top view from an RGB camera. And the environment itself is made up by a table with a shelf, which is a higher plane, and 3 objects. So the overall structure of the competition, of the overall challenge that one has to face to participate to the competition, is based on the intrinsic phase and the extrinsic phase. So in the intrinsic phase, the robot has to get knowledge from this environment by interacting with it in a free way. And it's given 15 million steps to acquire as much knowledge and skills as possible by interacting with this environment. The important thing is that in this intrinsic phase, the robot is not given any goal, any reward, any guidance. And so it has to be driven by intrinsic motivations, curiosity, and self-generated curriculum. Then we measure the knowledge that it acquired in the first phase by asking it to solve tasks that are structured, as I mentioned before. So there is an initial state that the robot has to face. We show to the robot a picture that represents a goal state, and the robot has to change the environment, so to bring its initial state towards, as much as possible, towards the goal desired state. The idea is that we assign to the robot several different tasks of this type. So each time it has to bring the environment from the initial condition to the goal condition. And each time we measure the distance between the condition that the robot managed to create and the goal itself. So the distance is an indication of how good the robot was in this particular task. We repeat this measurement for different tasks, and then we average over them. And what we get is a number that indicates the overall performance of the robot. In this respect, the competition is very important because it's a benchmark of open-ended learning, which is quite well defined. The idea is that in initial work, very often we used to say, okay, we ran an intrinsic phase and the robot came up with very interesting behavior. Look how nice they are. Okay, so that was the criterion to say that we were successful. But now with this benchmark represented by the competition, we can do much more than that, because we can have one number scoring the knowledge that the robot autonomously acquired in the intrinsic phase. And we can do this based on the trick that I mentioned of these sample tasks that we can draw from this environment and ask the robot to solve them for us. So let's get more formal on this and define the utility function that the robot is actually facing by facing the overall competition challenge. So the idea is that the utility function is measured and is referred to the extrinsic phase. And the idea is that the robot is assigned, for example, one task as the ones I mentioned before in terms of a particular goal that it has to achieve in this domain. And we measure its performance. And this performance is actually a sample of the performance that the robot is able to achieve with its policy. And the policy is goal indexed because, of course, for each different goal, the robot has to achieve implement different behaviors. Okay. And then what we do is we average this performance over different goals, as I mentioned. And these goals / tasks are drawn from this particular environment and are representative of all possible tasks that can be drawn from this environment. Okay. And the idea is that the robot should maximize this performance by searching the parameters of its policy. So you might think, how is it possible that the robot during the intrinsic phase manage to find out parameters that allow it to maximize the performance in the second phase? How is it possible that it can do this in the intrinsic phase when it does know nothing about the goals it will have to solve in the extrinsic phase? Well, it is possible because the environment is the same. So this means that during the intrinsic phase, the robot can explore the objects, understand how they work, their physical dynamics, and so on and so forth, and so acquire motor skills in order to control them. And then this knowledge is also useful in the second phase because the environment is the same and the objects have the same behavior. And so the robot can purposefully achieve desired goals. So this benchmark is different from what we can see in the literature. For example, the closest approach that we have found is meta reinforcement learning. And here, a robot is given a set of tasks, and it has to learn these tasks, and then is required to generalize and solve new tasks. This is quite different from what we are doing here, because here we have an intrinsic phase where we don't give any task, any goal, any reward function, as we mentioned, to the robot. And the robot has to self-generate task goals as to self-generate learning curriculum by itself in an autonomous fashion. And then use the knowledge it has acquired to solve the new tasks. So this is quite different from meta-reinforcement learning, which is the approach that we found that is most similar to our approach. Consider that the overall, this is one possible operationalization of open-ended learning problems, but there might be other ones alongside this one. What is important is that at least this one is a way that allows to have this strong benchmark on open-ended learning and can allow us to develop different models, to compare them, and to say which ones are better, why they fail, and so on and so forth. And so we think that the competition will foster the development of better and better models in open-ended learning. Now I leave the word to my colleague Emilio Cartoni, who will explain the competition details further, and will also explain a possible solution that we found to the competition that can be used as a baseline model for developing other more interesting models.
Hello everyone, I'm Emilio Cartoni, and I will now talk about the current edition of the REAL competition. REAL is an online competition and it is open to anyone. People can participate individually or also as teams. This year the competition is hosted by EvalAI, so to sign up you can go to the link in this slide or go to the EvalAI website, click on the Participate button and look for REAL 2021. The competition will run from August to December. And REAL is also sponsored by ICDL, the edition of this year and the next year. So the top 3 teams will receive a free registration for ICDL 2022. And they also will be invited to co-author a shared paper on the results of the competition. Gianluca has already anticipated what this competition is about. We created the REAL to establish a benchmark to compare open-ended learning approaches and also to foster research and new solutions in this field. How does the competition work? We have a simulated arm plus a gripper robot in an environment with a table and a few objects. Participants create their own controller for the robot, and this controller has to learn how to interact with the environment, undergoing 2 phases. A first long intrinsic phase, where the robot is free to explore and learn in the environment. Then a second short extrinsic phase, where the robot is given multiple tasks, one after another, in which it has to show that it has learned to manipulate the environment. Each task is scored, and the controller with the highest score wins. To participate in the competition and submit their robot controllers, participants are given a starting kit. The starting kit contains all the software necessary to run the simulation and also to make a submission. It also includes a baseline robot controller that participants can start from to make their solution. After having installed the starting kit, participants can develop their own controller by running both the intrinsic and extrinsic phase on their computers. They can then submit the controller to the EvalAI website for online evaluation. During the main phase of the competition, only the extrinsic phase will be run online. So you will have to send a controller that has already learned in the intrinsic phase running on your computer. In the final phase of the competition, instead, both the intrinsic and extrinsic phase will be run online during the evaluation, so it will be checked that indeed the controllers can learn from zero in the online evaluation. Indeed, the competition is structured in 2 parts as follows. A main phase that runs from now up to 15 December, where everyone can participate and where the agents, the controllers submitted by the participants, are trained locally and then submitted online to be evaluated. Only the top 10 participants or teams will then, at the end of the main phase, advance to the final evaluation. The final evaluation is a short 1-week round where each of the top participants can submit again their solution for a final evaluation where both the intrinsic and extrinsic phase will be run online. Code inspection. To be eligible for ranking, participants are required to open the source code of their submission to the competition monitoring check. This means that while the submissions are private, the organizer will still be able to check the code and see that participants are following the rules. This is especially necessary since for most of the competition, only the extrinsic phase is run online, but we have to check that these algorithms are actually algorithms that are capable of learning during the intrinsic phase and not just manually coded specifically for the tasks of the extrinsic phase. So this is how the environment looks like, with the robot arm plus the table with 1 to 3 objects. The arm is a 7 degrees of freedom arm with a gripper which has touch sensors on it. The robot has also a top-down RGB camera, which has a view as the one on the bottom right. Here. And then there is also a table with 1 to 3 objects on it. When submitting their controllers, participants can choose 2 versions of the environment, the easy or the hard one. The easy one has a couple more options that simplify the robot control and perception, and we will see later all the simplifications in more detail. Now, about the rules and limits, the intrinsic phase lasts 50 million time steps in the simulation. And to give an idea, each time step of the simulation equals to 5 milliseconds. So 50 millions is about 20 hours of simulated time, during which the robot has to interact with the environment and learn how to manipulate it. The extrinsic phase is divided into 50 goals, and each goal lasts 10,000 time steps. At the end of these 10,000 time steps, the current configuration of the object is compared to the goal, and the score is calculated. Then the objects are reset to a new position, and a new goal has to be achieved. Now, a critical rule of the competition, the golden rule, is that is the following. No information should be given to the robot about the task it will face, because this must be autonomous open-ended learning. The controller should learn from scratch to interact with the object using things like intrinsic motivation, self-generated goals, and other types of autonomous and open-ended learning. In particular, it is forbidden to use the scoring function of the extrinsic phase or variance of it as a reward function to train the agent. The controller should be able, in theory, to learn in any environment the robot is put in, regardless of the final task. As we said, after an initial intrinsic phase where the robot is free to explore the environment, the robot performance is scored in the extrinsic phase. In the extrinsic phase, the robot will have to complete 50 tasks, with each task having a different goal. Each goal requires the robot to move all the objects present in the environment, which may be 1, 2, or 3, to specific positions. Goals will belong to 3 different types. In the 2D goal type, the objects are always on the table plane and not on the shelf, the farthest part of the table. They will never be very close to each other, and they will have a fixed orientation. So this is the easiest type of goal. Then in the 2.5D goal type, the objects can be both on the plane and on the shelf. So to achieve them, the robot needs to learn not just to push the objects on the table plane, but also needs to learn how to raise them from the plane to the shelf or bring them back. Still, the objects will never, in the goal, will never be too close to each other, and they will have a fixed orientation. Finally, in the 3D goal types, their objects are set on both the table plane and the shelf. They can have any possible orientation and no minimum distance between them, so they can be one on top of each other. Each goal has a different starting condition, and the robot has a fixed time to achieve the goal configuration. After the time is up, The configuration achieved is scored according to how close it is to the desired goal configuration. When participants submit their controller, the synthetic phases run online and the score is calculated. You will be able to see the scores achieved in the online leaderboard for each type of goal, 2D, 2.5D, and 3D, plus the total score. And also these scores might appear twice in the leaderboard, since there will be one for the easy environment and one set of scores for the hard environment. The leaderboard will be ordered by taking the total scores, with the total score for the hard environment being ranked first, as it is an harder challenge. Participants will have many options available when running their controllers, and also some simplifications. These options apply both when testing the controller on your own computers and also when submitting the controller online. First of all, participants can choose if they want to control the robot with joint control or with position control for the arm, plus joint control for the 2 degrees of freedom gripper. Then the participants can also use in their algorithm a special on position to bring the robot back to its starting position with the arm being straight vertical. They can also choose how many objects are present in the environment, from 1 to 3. Having less objects is simpler, but gives less possibility to score points in the final task, since each object is scored independently and each object is valued at a certain number of points. Then participants can also choose not to use the gripper and leave it closed all the time, or when using position control, to keep the wrist pointing downwards at all time. This simplifies things, as the wrist pointing downwards make it more likely to interact with the table, but it also renders impossible to reach the shelf that is in the farthest part of the table, so it requires the wrist to be pointing towards it. And also the closed gripper leaves aside some consideration, but you cannot grasp the object. Finally, there are two important simplifications that are only available when choosing the easy version of the environment. When running the easy version of the environment, it is possible, actually it is possible. You will receive additional observation from the environment beyond the joint positions, touch sensors, and the camera image. You will also receive the X, Y, and Z position of each object, and also a segmented image where each pixel has a flag that specifies which objects it belongs to. So this greatly simplifies perception. At the same time, in this environment, it's possible also to simplify the control. As we're running this version of the environment, it's possible to control the robot by using macro actions. These macro actions are scripted push movements where the controller only has to choose a starting and an ending point on the table, and the robot automatically performs a push movement along the table using that segment. It can still miss the objects, since the starting and end point can be anywhere on the table. However, it is far more easier to hit objects by using this macro action that always push along the table, rather than controlling directly in the wall joint or Cartesian position space and trying to randomly hit the objects. Okay, so here we can see how the controller should look like at various stages of the competition. On the left, there is an untrained controller included, there is an untrained controller performing random movements in the joint space. Then in the center, you can see the baseline controller included in the starting kit. In this image, it is using the macro action we talked about before in this environment. As you can see, it performs push movements along the table, so its behavior is already pre-structured. But the baseline can also work in the hard environment using joint control. On the right, you see an ideal controller that has learned not only to push the objects, but also to grasp them and it is capable of handling all the three objects at the same time. Now, how to solve the competition, how to make the fantastic controller that can do anything. I will now describe you some of the challenges that participants have to face in the competition, and also a bit about the baseline controller that we have included in the starting kit. I will also point to some of the literature that can give ideas on how to build other solutions. So the competition presents many challenges that altogether make it very hard. How can the robot reach the objects? How does it know that the objects are there? And how does it know that interacting with the object is good? These problems are interdependent, and have to be solved at the same time. Now, the first problem, one of the first problems is that random exploration rarely leads to touching an object. So if you use joint control and randomly try to use it, the arm usually wanders around off the table. And here you can see in the picture an example of this, without touching objects. So some sort of intrinsic motivation is needed to guide the exploration towards the interesting part of the environment, those where you do make some changes, where you really change the environment and may learn something about it. One possibility is to use, for example, curiosity-driven exploration by self-supervised prediction, as in the article of Patak 2017, where the robot is naturally attracted to things that initially it cannot predict. So it would be, for example, attracted at first by its own arm movements seen in the camera. But after learning them, it would be more attracted by the objects that move on the table when hit. Of course, once it experienced them at least once. And so another problem is the object recognition. If the object has to learn everything from scratch, it does not know that the objects exist. And when it starts the intrinsic phase. So one possible solution that we have included in the baseline is to employ some sort of rational autoencoder, for example, to recover the objects, the presence of the objects as latent variables. However, the objects are by themselves static, so an autoencoder cannot be trained to recognize them just by looking at this still image forever. So you need first to reliably move the objects around so that the autoencoder has enough variety of images to then extract these latent variables. Also, when you move the object, the arm is usually in sight and it is big. So if you encode all the images, the autoencoder might favor encoding the arm, and it will be harder to, let's say, to need attention to the objects. Another problem is that in the intrinsic phase, there is no reward, no goals, and you should not give it information on the task that has to be performed. So if the robot wants to train itself to do something without rewards and goals from the outside, it has to self-generate tasks. A couple of interesting articles that we suggested for this competition are visual reinforcement learning with imaging goals by Mir in 2018, and Florenza 2018, automatic goal generation for reinforcement learning agents. The first article, the first approach, relies on having extracted some meaningful latent variables that you can sample from. And to make this work, you should, before take on the problem of being able to encode the objects, and then you can generate tasks about these objects over the latent variables. On the other side, the Florence approach is interesting because it has a notion of goals of intermediate difficulty. That is, try to set yourself goals that are not too hard, that are impossible to reach, but not too easy, that you actually not improving yourself. And then another of the problems is that these three problems and also others that I will not mention here actually interact together. And so, for example, to learn to move the objects, you must know that these objects exist. But to know that they exist, you need to move them first. So it's kind of circular. So schematically, you have these three things, the goal generation, the object recognition, and the control, and they all interact together. They all have to be solved at the same time. And another thing is that since you are trying to solve them at the same time, the algorithms that you will employ is also have to deal with unstable representation, since the representation you might have extracted early during the extrinsic phase might change during the extrinsic phase as the training progresses. And all in all, all these challenges are quite hard to take together, and usually means trying to build a complex architecture that has many modules that have to be coordinated together. To facilitate the participants, we have actually built such an architecture. We have included a baseline model in the software starting kit, and the baseline architecture has three modules: an abstractor module that creates abstractions, and an explorer module which suggests which action to use to explore the environment, and a planner module to reach the goals in the extrinsic phase when external goals are given, but might also be used by setting yourself goals in the extrinsic phase, although the baseline does not do this yet. And then how they are implemented, these modules. In the abstractor module, we have put a variation autoencoder to recover the latents, plus a dynamic abstraction module that creates multiple levels of abstraction over these latent variables. Then in the Explorer module, we have just let random explorer, which is good enough when using the macro action and adequately when using the joint controller in a specific way that you will see in the baseline. And then in the planner module, we used an A-star algorithm, which replants progressively with higher abstraction if it does not find a suitable plan on the lowest level of abstraction. It tries to have an higher one to generalize and try to find some solution. And okay. Here we will see how the baseline looks like and performs. You can see the intrinsic phase first. The baseline uses the macro action, so it does these push movements along the table, which not always eat the objects, but they eat it often enough to learn something. And during the intrinsic phase, it explores randomly, as we said, but it keeps track of what happens when the object is in a certain position, it does another action, and what is the outcome. And it records all this and to use it for learning. And then in the extrinsic phase, we can now see there is the goal, which is showed up here. And the baseline is able to more or less reliably move the objects towards the goal. Sometimes it does not go straight to goal. Sometimes it even pushes the objects down the table, but then it starts again and moves the object to the desired goal position. And so we have also an example of how the baseline works with the joint control. You can see in the intrinsic phase, the movements are quite a lot more creative. And as we said, it often moves just in the air without hitting anything. But sometimes it manages to catch the objects. And with this few amount of interaction, you can still learn something. And as you can see here in the extrinsic phase, it managed to use these very strange looking movements to hit the object and slowly, but not steady, but slowly try to move it towards the goal position. Again, sometimes it just throws off the object off the table, but you can see that it is indeed trying to move it towards goal. So you can achieve some score also with this, the baseline in the joint controller space. So using the harder environment version where the macro action is not allowed. Thanks for your attention. If this is live, then it would be question time. And I hope to see you in the competition and to see you improving this baseline and bringing a new and exciting solution to bring forward the field and win the competition. So see you soon and bye.